Hello everyone, I welcome you to my YouTube channel, Professor CivilMandal. Here I basically discuss about civil engineering and you will find various video lectures regarding various topics of civil engineering in my channel. So today I am bringing out a new subject, that is the fluid mechanics. So it is a very important subject when you are studying it as a civil engineering point of view. Also, this subject is very much essential to different other branches like mechanical engineering or chemical engineering. So even in civil engineering, this thing comes to very important use in further higher specializations like water resource engineering. So whenever we are speaking about fluid mechanics, so we are basically dealing with the property of the fluid, various properties of the fluids and various conditions which are being exposed to a fluid. So that includes all the forces basically acting on them. So whenever a fluid is at rest or it is at motion, or even due to its various kinds of properties, many kinds of changes or forces it will be observing amongst itself. So these are the things which we are going to study in fluid mechanics. So first of all, let's read the definition of the fluid mechanics. That is, fluid mechanics is the branch of physics or engineering concerned with the physical condition of fluids and forces acting on them. So as I said you that it will be totally concerned on the physical condition of the fluids, that what is the temperature, what is the density, what is the viscosity, and what are the forces that are acting on it, even if it is at rest or is it in motion. Okay, so what is basically fluid? A fluid is a substance that continually deforms under an applied shear stress or external force. So basically, if you are talking about fluid is such an element which actually continuously deforms under application of shear stress or external force. So whenever you consider, suppose, a particular element of fluid that is present and you are applying some force on it, suppose it is a shear force, and it is for sure the fluid is going to deform continuously. Okay, unlike solid which may or may not deform. Okay, so that's why we say that fluid is basically a substance which continuously deforms under application of the shear stress or external force. So fluids are a phase of matter that includes liquids, gases and plasma. So all kinds of liquids, gases and plasmas are basically fluids. So here one classification is given. So if you take up physics, then physics is divided into continuum mechanics and other branches. So what is basically continuum mechanics? Continuum mechanics is that branch of mechanics that deals with the mechanical behavior of matter modeled as a continuous mass rather than as a discrete particles. So in continuum mechanics we will consider that a body is a continuous mass of various particles. It's a continuous mass of various particles and not just a single or a unit of a discrete particles. So we will take up something bulk over it whenever we are considering the continuum mechanics. It is not like the quantum mechanics where we take smaller particles like photon, neutron, antineutrino, neutrino, etc. So continuum mechanics is a branch of mechanics that deals with the mechanical behavior of materials modeled as a continuous matter rather than a discrete particle. So we will take up the model as continuous matters. So physics is divided into continuum mechanics and various other branches. So in continuum mechanics it actually includes one other branch that is also the solid mechanics, which is basically known as the strength of materials. Basically we study solid mechanics when we are studying this subject known as strength of materials. So apart from that, the other thing which is there in the continuum mechanics is the fluid mechanics, and fluid mechanics is further divided into two, that is fluid statics and fluid dynamics. So clearly by the name you can see that fluid statics includes the forces or the condition of a fluid when it is in rest, whereas in fluid dynamics the same thing will be considered when the fluid is in motion. So again, fluid dynamics is divided in two branches, hydrodynamics and aerodynamics. There can be various other branches of fluid dynamics, but mainly we consider hydrodynamics and aerodynamics, where we consider the motion of water in hydrodynamics and the motion of air in aerodynamics. So considering that fluid is a continuum, the concept of continuum in fluid mechanics is the continuous distribution of mass in a body of matter that is without spaces. So if you consider the fluid mass very discretely, you will see that it is a continuous set of particles with minimum of the spaces between them. Okay, and therefore it is a continuous distribution of mass in a body of matter that is without spaces. The concept of continuum is generally applied looking at the fluid in macroscopic level. So we consider that the fluid is in macroscopic level and not in a microscopic level. So this gets help in determining the fluid as a point function, like plotting the velocity profile of a fluid, measuring the temperature of fluid particular point in the fluid, etc. So assumptions are valid considering the fluid at macroscopic level only. So you cannot consider the fluid to be microscopic, we will consider it as a macroscopic. So that is why we are considering the fluid to be macroscopic, because in continuum mechanics we consider the object or the material to be of some continuous mass. So that thing is only possible if the continuous mass is present in bulk, and which is solely present in the macroscopic level, not in a microscopic level. So therefore assumptions are valid considering fluid at macroscopic level only. So after we have this brief introduction about fluid and fluid mechanics, let us move on to the important part, that is the fluid properties. So first we come up with the mass density. So mass density is basically the specific mass of a fluid. Mass density of specific mass of a fluid is the mass which it possesses per unit volume. So basically it is the normal density which we deal as the mass per volume. Okay, so this is denoted by the letter rho. Its SI unit is kg per centimeter square, or it is actually kg per centimeter cube. It should be kg per centimeter cube. Next, moving on to the next property, that is the specific gravity. So specific gravity is the ratio of the specific weight of a fluid to the specific weight of the given reference, that is the standard material. So when you consider the specific gravity of a particular the specific weight of a particular fluid with respect to the specific weight of a given standard, so what we do represent as a standard, that is the specific weight of water at 4 degrees centigrade, and this is our standard material. And with respect to it, when we take the specific weight of the fluid, we get the specific gravity. So basically specific gravity is specific weight of the liquid upon the specific weight of water at 4 degrees centigrade. Why 4 degrees centigrade? The specific gravity for liquid is nearly always measured with respect to water at its densest, that is at the 4 degrees centigrade. So at 4 degrees centigrade, water is considered to have its densest state, and therefore it is, which is actually around 1000 kilogram per centimeter cube. So specific weight of liquid upon 9810 Newton per meter cube. So it will be taken as 9810 when it is multiplied to 9.81 meter per second square, that is the gravitational acceleration. Next is the relative density of one substance with respect to other substance. It is actually the ratio of the density of one substance with respect to other substance. Suppose we are going to consider the density of one particular oil, so with respect to water it has this much of density. So when we are comparing two liquids, we take up the relative density, and similarly we also take the specific gravity when we are comparing. Next comes the specific weight. The specific unit of a fluid is the weight it causes per unit volume. So the weight of the fluid per unit volume is the specific weight. So just do not confuse it with mass density. Mass density is the mass per unit volume, whereas the specific weight is the weight per unit volume and denoted by the letter gamma. For water it is gamma W and its SI unit is Newton per meter cube. Next is the specific volume. Specific volume of a fluid is the volume of the fluid per unit weight. It is the reciprocal of specific weight, that is, and thus the SI unit is meter cube per Newton. So specific volume of a fluid is basically the reciprocal of the specific weight. So actually here we can say that it is volume upon the weight. So therefore the SI unit comes out to be meter cube per Newton. So let us take up a problem. So we have a problem, that is the 3 liter of petrol weighs 23.7 Newton. Calculate the max density, specific weight, specific volume and specific gravity of petrol. So whatever definitions which we have learnt now will all be applied over in this problem. So the mass density, let us consider the mass density first. The mass density of petrol, that is rho p, let us take it as rho p, will be mass by volume. So how to get the mass? Mass is basically the weight 23.7 upon the gravitational acceleration, that is 9.81, upon the volume which is given as 3 liter. So upon calculating this we will get it as 0.805 kg per liter, because this is in kg and this will be in liter, and which is actually 805 kilogram per meter cube. Next is the mass density of water. Mass density of water, let us take it as rho W, and it will be given by, it is actually 1000 kg per meter cube. You can take up it as that. And specific gravity of petrol will be, so it is 805 upon 1000. So specific gravity is basically the ratio of these two, and it will be 0.805. again specific weight of petrol, that is weight per unit volume, and that will be equal to 23.7 upon 3, that is 7.9 newtons per liters, which is 7.9 newton, sorry, it will be kilonewton per meter cube. Okay, if you are having any kind of confusion, just keep it in mind. 1000 liter is equal to 1 meter cube, and everything is based upon all these things. Next is the specific volume, which is volume per unit mass. It is given by 1 upon rho p, which is 1 upon 805, and it will be somewhere around 1.242 times 10 to the power minus 3 meter cube per kg. The next topic is the next property is a very vital property, and it does have some wider use when you will be reading with it in the very next chapters. This is viscosity. The viscosity of a fluid is a measure of its resistance to shear or angular deformation at a given rate. So whenever a fluid will be given some shear, fluid element will be given some shear force, so it will be trying to resist it before moving it in that direction of which the force is being applied. So it is basically the measure of its resistance to the shear or angular deformation at a given rate. So it is a resistive force. Just like friction, viscosity is another resistive force. So friction is the thing which you observe in solids. Viscosity is found in liquids, and friction is between two different material, whereas viscosity can be within the same liquid or the same fluid and in its various layers. So if we take up a fluid element and distribute it among various layers, so even these minute layers will have viscosity whilst sliding against each other. So it is primarily due to the cohesion and molecular momentum exchange between fluid layers. So more will be the cohesive force, that is, more will be the attraction between the like particles, similar particles of the fluid, or more will be the attraction between the fluid particles itself. So it will induce more amount of viscosity, and thus molecular momentum exchange between the fluid layers. So Newton gave a law regarding viscosity which states that the shear stress between the adjacent fluid layers is proportional to the velocity gradients between the two layers. So what is the velocity gradient? Velocity gradient is basically this term. This is the change in velocity with the change in gradient. Okay, so du is the change in velocity and du is the change in velocity upon dy is the change in the gradient. So this is basically velocity gradient, and the viscosity, the shear stress between the adjacent fluid is basically proportional to this velocity gradient. So to remove this proportionality constant, we introduce a coefficient known as the viscosity or the coefficient of viscosity. So mu is the viscosity, tau is the shear stress, and du upon dy is the rate of shear deformation or the velocity gradient. So the ratio of the shear stress to shear rate is constant. So this is constant, the ratio of shear stress to shear rate for a given temperature. So this ratio of shear stress to shear rate will be constant for a particular temperature only, and the same thing may not be valid if the temperature is altered. And similarly with pressure, it will be taking place with a particular pressure only, and the results can be different if the pressure is again altered, and also the same is true for temperature. And it is defined as a viscosity or the coefficient of viscosity, and this thing, the ratio of shear stress to shear rate, is basically defined as a coefficient of viscosity. So just take up this one. If you take up this tau and divide it upon this du upon dy, so this will be giving you this constant, that is mu, which is basically, you can say, is the coefficient of viscosity. So again, there are two types of viscosity. One is the dynamic viscosity and another is the kinematic viscosity. So dynamic viscosity is a tangential force per unit area required to move one horizontal plane with respect to another plane at an unit velocity when maintaining an unit distance apart in the fluid. So while maintaining a unit distance apart in the fluid with respect to another plane at an unit velocity, the tangential force acting per unit area will be your dynamic viscosity. Okay, then comes its unit, that is Newton second per meter square, and or you can say it to be Pascal second or Poise. This is in SI unit. And next is the kinematic viscosity. It is the ratio of dynamic viscosity to density, a quantity in which no force is involved. So basically, whenever we are considering the forces, then we are using the dynamic viscosity, but whenever we are not considering the forces, then we are using the kinematic viscosity. So the basic difference is that there is an application of force whenever it comes to the dynamic viscosity, and secondly, the kinematic viscosity is basically the ratio of dynamic viscosity and the density of the fluid, and therefore its units are meter square per second or centimeter square per second. So there are two types of fluid again. One is the Newtonian fluids, which actually obey the law of viscosity, like the water and air, and again it is found that there are various liquids which don't obey the Newton's law, and that is they are known as a non-Newtonian fluids. So just go through this chart once, it shows a comparison of non-Newtonian, Newtonian and viscoelastic properties. So basically there are time dependent viscosity and time independent viscosity and viscoelastic material. So viscoelastic material are the Bingham plastic, which actually behave as plastics and are quite similar to the Newton's law of viscosity to a certain extent. So you can see the equation, that is tau is equal to tau naught plus mu P upon du upon dy. So this part is quite similar to the Newton's law of viscosity, but this thing, there will be an additive constant. So the Newton's law of viscosity will be obeyed by this type of fluid after a certain extent, and therefore they are known as the Bingham plastic fluid, and they behave like solid at first, that is until this stage, until this barrier is broken, and then they flow like Newtonian fluids. Next is the time dependent viscosity. Time dependent viscosity includes the rheopectic and thixotropic fluids. The rheopectic fluids apparent viscosity increases with the duration of stress, and for them the apparent viscosity decreases with duration of stress, and it is all because the n is greater than 1 for rheopectic fluids and less than 1 for thixotropic fluids. Again, we have the time independent viscosities, that is the shear thickening or the dilatant fluids, or the shear thinning or the pseudoplastic fluid. Why they are shear thickening? Because the apparent viscosity increases with increased stress. So whenever we are increasing the stress, the apparent viscosity keeps on increasing, and the apparent viscosity decreases with increasing stress for the pseudoplastic fluids. It is all because n is greater than 1 and n is less than 1. Why this n thing is being considered? It is considered in this particular equation. This is a generalized equation, and if the n is less than 1, then we have either the shear thinning fluids or the pseudoplastic fluids, or we have this thixotropic fluid. But when it is greater than 1, then we have rheopectic and dilatant fluid. So this is the equation, and whenever there is an additive constant to it and n is actually equal to 1, like your Newtonian fluids, then it is the Bingham plastic, which partially follows the Newtonian law of viscosity. So here is the graph. It is totally based upon the equation which we have shown for the Newtonian and non-Newtonian fluids. You can see is a complete straight line, this Newtonian fluids, and it is all because it's just du upon dy, and there is no exponent over it. And whenever the dilatant fluid which has an exponent greater than 1, so we therefore have an increasing shear stress with respect to the deformation rate. And similarly, pseudoplastic fluid have the value of n less than 1, and therefore we have a decreasing curve. Similarly, we have the same thing for thixotropic and rheopectic, but the thing is that there will be a certain amount of shear stress already prevalent in that fluid before they start showing shear deformation. Okay, so at first they won't be moving, and after certain application of the force or the stress, they will start moving. You can also go through the examples of various types of fluids, like here given in this chart, and the notes will be given to you in the description. So let us just proceed to do one problem regarding viscosity. The question says that find the kinematic viscosity of an oil having density 981 kg per meter cube, and the shear stress is given at a point as 0.2452 Newton per meter square, and the velocity gradient at that point is 0.2. So we have what is given to us, that is the density rho as 981 kg per meter cube, and shear stress, this is mass density, shear stress tau is given by 0.2452 Newton per meter square. Okay, and also the velocity gradient du upon dy, that is 0.2 per second. So using Newton's law of viscosity, that is tau is equal to mu du upon dy, or we have tau as 0.2452, it is given u times 0.2, therefore mu equal to 0.2452 upon 0.2, and that is 1.226. Just take care of the unit, that is Newton second per meter square. Therefore, and this mu is actually the dynamic viscosity. Therefore, the kinematic viscosity will be, that is represented by nu, will be mu upon rho, and that is 1.226 upon 981, which is equal to 0.125 times 10 to the power minus 2 meter per second, meter square per second, which is actually 112.5 centimeter square per second. It is 12.5 strokes. In the next question, we have given the velocity distribution of flow over a flat plate as u is equal to 3 by 4 y minus y square, in which u is our velocity in meter per second at distance y meter above the plate. So basically you can say it is a velocity profile, that is basically a graph between u and y. Determine the shear stress at y is equal to 0.15 meter. So what we have to do, we have to determine the shear stress at y equal to 0.15 meter. Take the dynamic viscosity as 8.6 poise. Okay, so first of all, just consider that we are given a velocity profile something like this, a relation between u and y, and we are asked to find the shear stress at a point, suppose 0.15. so it will be more convenient if we obtain the velocity at this particular point at y equal to 0.15, and at the same time we apply this on the equation, that is the Newton's law of viscosity. Okay, so to get that, we can take that u is equal to 3 by 4 y minus y square. So if we differentiate it with respect to y, we will get it as du upon dy equal to 3 by 4 minus 2y. It's nothing just but a simple differentiation. So therefore we get this as this is the nothing but our shear deformation, or you can say it to be our velocity gradient. So now what we can do is that at y equal to 0.15, at y equal to 0.15, you will have du upon dy equal to 3 by 4 minus 2 times 0.15, and it will be equal to 0.45. So at y equal to 0.15, du by dy, or the velocity gradient will be 0.45. And also given viscosity mu is equal to 8.5 or 8.6 poise, which is basically 8.6 upon 10 Newton second upon meter square, because 1 poise is equal to 1 Newton second per meter square. So we have the velocity gradient, we have the viscosity, and thus we can obtain our shear stress. That is, therefore, shear stress, that is tau, is equal to mu times du by dy, that is our velocity gradient, and it will be equal to 8.6 upon 10 times 0.45, and it is Newton per meter square, and therefore it will be around 0.3825 Newton per meter square. So moving on to the next question. Through a very narrow gap of height h, so let us consider this as a narrow gap of height h, a thin plate of large extent is pulled at a velocity v. On one side of the plate is oil of viscosity mu1, and on the other side of the oil of viscosity mu2. Calculate the position of the plate so that the shear force on the two sides of the plate is equal and the pull required to drag the plate is minimum. So in this case, there is a thin gap within which there is a very thin plate, and it also has two different fluids in its both sides. So we are asked to find the shear force on the we are asked to find the position of the plate so that the shear force on the two sides of the plate is equal and the pull required to drag the plate is minimum. So there are two conditions which we have to use. We have to find out the position of the plate. So let y be the distance of the thin plate. So we will consider this y to be the distance of the thin plate. Now force per unit area on the upper surface of the plate is given by mu1 du upon dy, because on the upper surface of the plate we have the oil with viscosity mu1, so it will be mu1 du upon dy, and velocity is given by v, so we will take v in place of du, and in place of dy we will have h minus y, because we have considered this length to be y, and therefore this will be h minus y. Similarly, the force per unit area, the force per unit area on the bottom surface of the plate will be equal to mu2 times What will be du? It will be same, that is velocity v, and it will be y. So let us consider this to be equation 2 and this to be equation 1. So equating 1 and 2, we get mu1 v upon h minus y equal to mu2 v upon y. So from here you can get, on solving this we will get y equal to mu2h upon mu1 plus mu2. Now in the part 2 of the problem, we are asked to find the position when the pull required to drag the plate is minimum. So we can consider that the pull will be due to the force which will be the sum of both of the shear stresses, that is mu1 v upon h minus y plus mu2 v upon y. So we are considering that the pull that will be required to drag the plate will be equal to the sum of forces due to the stresses, sum of shear stresses due to both the oils on the two different sides of the plate. So again, for F to be minimum, we know dF by dy shall be equal to 0. Simple mathematical concept. So therefore dF upon dy will be, so upon differentiating this equation with respect to y, we get mu1 v upon h minus y square minus mu2 v upon y square, and that is equal to 0. So if we solve this equation, we will get y equal to h upon 1 plus square root mu1 upon mu2. So that's all for this video, and the later part will be continued in the next part of the video regarding the properties of the fluid, and there will be starting with surface tension, a new property of fluid. Thank you. Please like, share my video and subscribe to the channel if you are new.